All right, welcome everyone to this week's Autonomy Talk. This week is a pleasure to have with us Professor Majumdar, who is an assistant professor at Princeton University in the Mechanical and Aerospace Engineering Department. So something about Ani, he got his bachelor's in mechanical engineering and mathematics from University of Pennsylvania. He then moved to MIT, where he got his PhD in electrical and computer science, and then did a postdoc at Stanford, the Autonomous Systems Lab. His research focuses on control of highly agile robotic systems, such as unmanned aerial vehicles. So this means today we will see probably fancy videos. And he focuses on formal guarantees on safety and performance of these systems. Now, as you can see from the bio, I sent you one a very big number of awards, actually some of them even twice. So I'm not going to list all of them. I mentioned just the NSF Career Award and some Best Paper Awards at ICRA and IJRR. Today is going to talk about safety and generalization guarantees for learning-based control of robots. And we are very interested into the topic. So I look forward to the talk. The stage is yours, Ani.
All right. Yeah, thanks so much for the introduction and for the invitation to present. Yeah, I'm really excited to present our work on this topic. So overall, in our group, we think about how to control agile robots and trying to make sure that they operate with guaranteed safety and performance, particularly in complex environments. So the last few years, we've seen a tremendous amount of excitement around machine learning in robotics, deep learning in particular. And we've seen kind of applications of these techniques in many different domains, from robotic manipulation, home robotics, UAVs, and also, of course, autonomous vehicles. And I think a lot of this excitement around machine learning and deep learning in particular comes from the power of these techniques to handle rich sensory inputs, such as vision or depth. So these techniques are pretty good at taking kind of raw sensory inputs, such as vision, and processing them into representations that can then be used for downstream tasks, such as planning and control. And I think we've seen some pretty compelling kind of empirical demonstrations of these techniques in many robotics applications. And I think while this is extremely exciting as a roboticist, this kind of adoption of deep learning techniques also brings with it a number of fundamental technical challenges. So the main challenge I'm going to focus on today is the challenge of safety. So how can we provide some formal guarantees, of course, under some assumptions, on the safety and performance of these deep learning enabled robotic systems? So there's been some kind of work on this topic over the last 4 or 5 years. Most of this work goes under the umbrella of what I would call safe learning, where the kind of typical problem formulation is to ensure that your robot doesn't violate any safety constraints during the learning process. So just to make this a little bit more concrete, imagine you have a drone and you're learning to perform a certain maneuver in a particular environment. So in the safe learning formulation, what you would try to do is make sure that as you're learning, as the policy is getting updated, the robot doesn't violate any safety constraints. So for example, it doesn't crash into the obstacles or the ground as it is learning. And there have been a number of approaches to address this safe learning problem formulation. So for example, based on Hamilton-Jacobi reachability theory, robust MPC, Gaussian process regression, and also formal methods. One thing I want to emphasize with this safe learning formulation is that the typical problem formulation considers safety during the training process. So typically you think of the environment that the robot is operating as being fixed. The thing that's changing is the policy. So as the robot is learning, it's updating its policy, it's doing something different. And in the safe learning formulation, we want to make sure that the robot doesn't violate any safety constraints during this learning process. What I'm going to focus on in this talk is a little bit kind of complementary, a bit different to the safe learning formulation. So instead of thinking about maintaining safety during the training process, what I want to think about is safety during the testing process, testing or deployment in new environments. So environments that the robot has not seen during its training phase. So this is really the problem of generalization. So how can we ensure that these deep learning based methods are going to generalize to previously unseen environments? So again, just to make this concrete, let's think about a kind of running example that I'll use throughout the talk. So imagine you have a drone and you're trying to learn, let's say, a vision-based obstacle avoidance or navigation controller. And let's say you're doing this kind of end-to-end. So this neural network is going to be trained to take in raw sensory inputs like vision or depth and process them into actions for the drone in order to avoid obstacles or maybe navigate to some goal. And let's say you've collected some data set of different environments. So in this case, these are building scans that someone has kind of gone around and spent a bunch of effort to collect these different environments. Let's say you have some finite data set that's kind of representative of the environment that you want to deploy your system on. And you train your neural network system to kind of avoid obstacles or perform navigation with these 1,000 environments. So the question we're interested in is what happens when you take this trained system after some learning process and you deploy it on a previously unseen environment. So you deploy it on the 1,001st environment. The question we're interested in is how can we guarantee that the robot will succeed, maybe with some high probability, in this previously unseen environment. So to give you a sense for why this is challenging for kind of current robotic systems, this is one of Tesla's autonomous vehicles that's driving down a highway kind of at evening time. And if you see the output of the perception system, it's really interesting. So it's actually seeing the sun that's kind of low down in the sky, and it's interpreting that as a yellow traffic light. And that's actually causing the car to try to slow down, to try to brake. In this case, the human driver is paying attention, and you can kind of see at the bottom of your video that the driver is overriding this braking command and making the car go forward still by pressing the gas pedal. But if this was fully autonomous, then this could have potentially led to a bad scenario with the car just coming to a halt in the middle of a highway because of this kind of incorrect, this inability to generalize to the specific situation. This is another one of Tesla's vehicles. Maybe you've seen this video. This was recent, a couple of months ago, where one of the cars in kind of summon mode crashes into a $3 million private jet. And again, I would argue that this is a failure to generalize. So these systems are trained, these perception systems are trained with lots and lots of data, but the kind of output of that perception system is failing to generalize to this object, which maybe there weren't many instances of in the training data set. And we see this not just in autonomous vehicles, but in other application domains as well, for instance, robotic manipulation. So I think generalization is still a major challenge for robotic manipulation. If we're kind of generalizing to different object geometries, or in this case, with the OpenAI Rubik's Cube system, even different initial conditions, the variation in initial conditions is kind of enough to mess up the robot's policy. So the task success rate for this task for OpenAI system range from about 20% to 60%, depending on what initial conditions you set up the Rubik's Cube in. So I would argue that current learning-based robotic systems fail to generalize to even mildly different environments from what they were exposed to during the training phase. And I see this problem of generalization as a really fundamental technical challenge that we need to understand if we want to think about guaranteeing safety for learning-based robotic systems. So the last few years, there's been some effort, particularly in the reinforcement learning community, that tries to improve generalization performance via a multitude of different methods, for example, based on domain randomization, data augmentation, regularization by simulation, and so on. Most of these efforts are kind of empirically focused, so the goal is to demonstrate via experiments that you get some improvement in terms of generalization. What I'm going to focus on today is not so much demonstrating that we can get really strong empirical generalization performance, although that's, of course, an important goal as well. The main focus today is going to be to try to understand how we can provide some formal guarantees on generalization for deep learning-based robotic systems. So this is the question we're going to consider. So how can we guarantee with some probability that your robot will succeed in a previously unseen environment under some assumptions that I'm going to lay out in a couple of slides. And I want to focus today on approaches for making generalization guarantees for robotic systems that have nonlinear or hybrid dynamics, so drones or robotic manipulators. rich sensory inputs such as vision or depth, and also neural network-based control policies. And my goal basically today is to try to convince you that we have some relatively powerful theoretical machinery that makes it at least possible to provide some non-trivial and meaningful guarantees for such robotic systems. Okay, so here's the formal kind of problem statement. So your robot has some dynamics. X is the state, U is the control input, and E is the environment that the robot is going to operate in. So I'm going to use the word environment pretty broadly here to refer to factors that are external to the robot. So if you're thinking about a UAV navigating, you can think of the building that the UAV is navigating through as corresponding to the environment. If you're thinking about robotic manipulation, then the object that the robot is going to manipulate, you can think of that as corresponding to the environment. The main assumption that I'm going to make, at least for part of the talk, is that we have some unknown distribution that I'm going to call D over the environments. So of course, this is a really complicated distribution, the distribution over all buildings that your robot might encounter, or the distribution over all objects that your robot might want to manipulate. I'm just going to assume that there is some distribution. We don't necessarily know what that is, but we have some data set, which I'm going to call S, of finitely many environments that are drawn from this underlying but unknown distribution over environments D. Your robot has some sensor. Again, we're particularly interested in rich sensing modalities like vision or depth. And the goal is to learn some control policy given this data set of environments that maps sensor observations or histories of sensor observations to control inputs in order to minimize some cost. So I'm going to denote C pi E. This is the cost of deploying policy pi on environment E over some finite time horizon, let's say. And I'll assume for some technical reasons that the cost for any policy on any environment is bounded between 0 and 1. So in the context of obstacle avoidance, you could think of a cost that assigns 1 if your robot crashes into an obstacle, or a cost of 0 if the robot kind of successfully navigates to some goal. And potentially you could also assign costs that are kind of in the range between 0 and 1. And finally, I'll assume that for any policy, we can evaluate the cost of the policy on our training environment. So we can take any policy, we can run it on our training environments, and we can kind of see how well any policy does on our training environments. So here's the kind of formal problem statement. So the goal is to learn a policy pi in order to minimize the expected cost across new environments that are drawn from this unknown distribution D. In this talk, it's going to be useful to work with a slightly more general problem formulation. So instead of trying to find a single kind of deterministic policy pi, we're going to try to learn a distribution P over policies. So in this formulation, there are 2 expectations. The inner expectation is because we're randomly choosing a policy from this distribution P that we're going to learn, given the data set of environments that we have. The main challenge is the outer expectation. So we don't know exactly what this distribution D is. We know it exists. We have some data set, but we want to say something about the expected cost on future environments that are drawn from this underlying distribution. The main technical tool we're going to use in this talk is what's known as generalization theory. So this comes from theoretical machine learning. And these techniques have primarily been developed in the context of supervised learning, so things like image recognition tasks. And the main kind of technical idea here is going to be to take these techniques from supervised learning and translate them, extend them to the kind of policy learning setting that I described. What this will allow us to do is come up with upper bounds on the quantity that we're interested in. So we're going to be able to upper bound the true expected cost across future environments that your robot will encounter from this unknown distribution D. And the algorithmic approach then will be to basically find a policy or a distribution over policies that minimizes this upper bound. So that gives you the best possible guarantee on generalization. And we can do this sometimes via convex optimization, or more generally via stochastic gradient descent or black box optimization techniques. So before I go into kind of more detail on the techniques, I just want to make a philosophical point, which has to do with what do I mean by guarantees or probabilities in this talk. So when I talk about guarantees here, what I'm referring to are frequentist style guarantees. So we want to be able to say that if I take my drone and I deploy it on 1 million environments, I want to be able to say that the drone is not going to kind of collide with 95 or 99% or higher probability. And we want to be able to kind of do this experiment. So if I ran the robot in 1 million environments, I want to be able to validate the bound or the guarantee that I compute from the theory. And I think this is different from Bayesian style probabilities. So for example, based on Gaussian process regression. So I would argue that if we're thinking about safety in robotic systems, what we really want are frequentist style guarantees. We want to be able to say that if I deploy my robot in many, many different environments, this is the probability of some unsafe behavior. And this is different from Bayesian style probabilities, which are inherently tied to the correctness of some prior. And so, for example, if your Gaussian process says 95% confidence, this doesn't necessarily mean that if you deploy your robot in 1,000 environments, 95% of the time you're going to be successful, because the prior may not kind of correspond to reality. And so the bounds you get may not correspond to any frequentist style bounds. At the same time, Bayesian reasoning allows us to incorporate some prior knowledge, inductive biases into our system. So ideally, we want something that still allows us to incorporate prior knowledge, but at the same time gives us frequentist style guarantees. And ideally, we want a technique that such that if we have kind of more reflective inductive biases, better prior knowledge that really reflects the ground truth, then that should lead to stronger frequentist style bounds. So the particular theory we're going to use is called pack-based theory, which actually gives us the best of both worlds from frequentist style reasoning and Bayesian style reasoning. So the pack stands for probably approximately correct. So that's the frequentist part and Bayes theory. Again, these techniques have primarily been developed in the context of supervised learning, things like image recognition tasks, and they provide some of the tightest known generalization bounds for classical supervised learning techniques such as support vector machines. And over the last 4 or 5 years, there's been a resurgence of interest in pack-based for explaining and also promoting generalization in deep learning, again, specifically for supervised learning problems. So what I want to do is just give you a quick kind of crash course in pack-based theory. So I want to make sure if you haven't seen pack-based before, that you leave the talk having understood at least the main kind of result from pack-based. So I'll first describe pack-based in the context of supervised learning, and then I'll describe how we can extend it to a policy learning setting that we're interested in. So in the supervised learning setting, we have an input space and a label space. So you can think of the input space as corresponding to the space of all images that you might want to classify. The label space corresponds to different object categories, let's say. Again, we're going to say that there's some unknown distribution D over your inputs. So this is the distribution over images that your system might encounter. We don't know what it is. We're just going to assume that there exists one. We're going to work over some particular hypothesis space. So think about neural networks that have a particular architecture that are parameterized by weights W. And we have some loss function that tells us how well any particular hypothesis does on any given example. So pack-based theory applies to learning algorithms that have the following kind of general structure. So instead of finding a single hypothesis, as is typically the case in supervised learning, we're going to optimize or learn a distribution over hypotheses. So think about this as corresponding to a distribution over weights of your neural network. That's what we're going to try to learn. So before doing anything, the first thing we're going to do is to choose a prior distribution P over your hypothesis space. So again, think of just specifying some prior distribution over the weights of your neural network. We then observe some data samples, so a finite number of images and corresponding labels. And based on the data set and the prior we choose some posterior distribution over the weights of the network. So this doesn't have to be the Bayesian posterior. This can be any posterior that depends on the prior and the data set in any way that you want. So that's the general structure of learning algorithms that PAC-Bayes kind of says something about. And the main result from PAC-Bayes basically relates the training loss, so the expected loss on the training data set corresponding to this posterior distribution P that we're trying to learn. So PAC-Bayes is going to relate that to the true expected loss, which is the quantity that we really care about, which is the expected loss on future data, future images, for instance. So the training loss we can compute given the training data set. The true expected loss we cannot compute directly. So here's the main result from PAC-Bayes. So it says that with probability 1 minus delta over the sampling of your training data set, delta is a parameter that you get to choose, we can upper bound the quantity that we're interested in. So we can upper bound the true expected loss as a combination of the training loss, which we can compute, plus this additional complexity term. So you can think of this as the kind of regularization term that's penalizing deviations of the posterior P from the prior P0. So the main term here is the KL divergence. And this is basically saying don't make the posterior go too far away from the prior in order to just make the training loss small. So this gives you a kind of balance between fitting the training data set that you have, minimizing the training loss, and a complexity term, a regularization term. And it turns out the summation of these two, the training loss plus this regularizer term, gives you a bound on the quantity that we care about, which is the true expected loss on future images that are drawn from this underlying distribution D, which we don't have direct access to. All right, so maybe let me just pause here for a second and see if there are any questions so far, either on the result or I guess any of the problem formulation. Okay. All right, so that was the main result from PAC-Bayes in the supervised learning context. So the main idea basically behind our work is to take these results and translate them into the policy learning setting that I sketched a few slides ago. So again, in the supervised learning setting, we have some input, maybe corresponding to an image. We have a hypothesis that takes the image, maps it to a label. We have a loss that tells us how well we did on the image. And PAC-Bayes then gives us a guarantee on the expected loss on new images. We're going to take the policy learning setting and basically map it to the supervised learning setting. And we're going to do this by thinking of the environment that the robot is operating in as corresponding to the input. The policy is corresponding to the hypothesis. So the policy takes the environment and kind of maps it to actions. This mapping is indirect, so it's through sensor measurements. But for any given environment, if you deploy a policy, that's going to lead to a certain number of actions. And then based on the actions, we can evaluate the cost that the policy incurs on the environment. So again, think of a cost of 1 if your robot collides, or a cost of 0 if the robot doesn't collide and reaches the goal. So with this mapping, which I've kind of presented only informally, PAC-Bayes allows us to guarantee the expected cost on new environments that are drawn from this unknown distribution over environments. So this is the formal result. So it's pretty much analogous to the supervised learning result. So we have the training cost. This is the cost on the training environments, which we can evaluate just by running policies on our training environments. The true expected cost is what we care about bounding or minimizing, which we cannot kind of compute directly because we don't know the distribution D. And the main result is that with probability 1 minus delta, again, delta is a parameter that you get to choose, we can upper bound the true expected cost as a combination of the training cost plus the same regularization term. So the algorithmic approach then is to basically find some distribution P. Again, this is a distribution over the weights of your neural network policy. So we want to find some distribution P that gives us the best possible guarantee. So basically minimizes this upper bound that we get from Pack-Bayes. So this is an optimization problem in certain cases, particularly if you're working with finite policy spaces and you want to find some distribution over a finite policy space. You can solve this optimization problem using convex optimization in more general settings, which is typically what we care about for like neural network-based policies. What we do is parameterize distributions over the weights of the neural network. And then we can search for a distribution P that minimizes the upper bound from Pack-Bayes, either using stochastic gradient descent or black box optimization, so derivative-free optimization. So basically, at the end of this process, we end up with two things. So the first is a distribution over policies, capital P, which we can run in future environments. And the second thing is a certificate. So this is the upper bound on the true expected cost on future environments that comes from this Pack-Bayes bound. All right. So that's the main kind of theory. Hopefully, the main result was clear. I'm going to present some results now, trying to demonstrate that we can get some pretty meaningful guarantees with this theory on different problems. So the first example I'm going to consider is a drone obstacle avoidance or navigation problem. So for these experiments, we're using the Parrot swing drone, which is a kind of hybrid between a fixed wing and a quad rotor. In this case, the sensing is going to be a depth image that's taken from the perspective of the drone. The drone itself is too light to have an actual depth sensor. So what we're doing here is simulating a depth image. So we have off-board motion capture cameras, and we're using that to simulate the depth image that the robot would have seen if it had a depth camera on board. So this is kind of what a typical depth image, simulated depth image looks like. And we're going to train a neural network-based control policy that takes the depth image and maps it to a motion primitive. So we have a finite number of different maneuvers that the robot can execute. So the neural network takes the depth image that it sees and maps it to a motion primitive that then gets executed on the hardware. This is trained purely in simulations. We have a data set of different environments that we use our Pack-Bayes machinery to train a policy with a certificate of generalization, and then we deploy it on the actual hardware system, as we're going to see on this slide. So the guarantee we get from Pack-Bayes for this problem with 1,000 training environments, so that's the capital N, is 93%. So that's a 93% success rate. The empirical success on the physical system, so we did 30 different trials in different environments, and the empirical success rate is 28 out of 30. So that's roughly 93.3%. So we see that the kind of bound we get from Pack-Bayes actually translates to the real hardware system, which is nice to see. So here are some representative videos of the drone. So these are operating in previously unseen environments, so environments that were not seen during the training phase. So it does crash. I guess it's important to show the failures as well. All right. So one question I haven't addressed yet is how do we specify the prior? So I mentioned that you need to choose some prior over the weights of your neural network, and then you choose a posterior based on that prior and the data set. So as I mentioned before, I think the prior provides an opportunity to embed some domain knowledge, so some prior knowledge that you have either on the environment that your robot will operate in or the physical system itself. For the previous example, we chose relatively simple kinds of priors. So for the drone example, we had a kind of base policy that we handcrafted that just scores different motion primitives based on the depth. And then we have a residual policy that we learn. And we just make the mean of the residual policy 0, and then place some kind of a standard deviation around the weights of the neural network that we're learning. Another approach that we've explored is to learn the prior itself. So for example, using imitation learning. So we did this in a manipulation context where we have a Franca Panda arm with a RGPD camera that's overhead. We collected demonstrations of grasping of different objects using a 3D mouse. So these are demonstrations from a human. We use these demonstrations to learn a prior over the weights of some neural network policy. And then we have a data set of different objects that we use that we use our kind of back-based theory to train a posterior distribution using. So the training for this example, again, was purely in simulation, and then we deploy it on the hardware system on a number of different objects, in this case, mugs that were not seen during the training phase. Again, in this case, the bound on success that we get from our back-based theory is approximately 93%. The prior, which is learned purely from imitation data from human demonstrations, achieves roughly a 83% success rate in simulation. The posterior, which we get from our back-based theory, gets a success rate of around 98% in simulation. And then we tested this on hardware. So the numbers you see on the table are 3 different random seeds on hardware. So we get a success rate of 100%, 100%, and 96%. So we actually see the bound again that we get from back-base being kind of valid on both in simulation and also in the hardware system. Another kind of application domain we've applied this theory on is quadruped navigation. So in this case, this is the Ghost Robotics Spirit robot. This has a RGPD camera that's on board, so you can see what the robot is seeing, the first-person view in the top left of the video. And the goal here is to start off in some initial state and kind of navigate to some specified goal location. And again, this is operation in an environment that was not seen during the training phase. So I'll show you what the training environment looked like on the next slide. But this is basically showing the trained policy operating in previously unseen environments. So these are the training environments we use. So this is a pretty diverse set of indoor environments. Again, we used 1,000 different training environments. We optimized a posterior distribution in order to optimize the back-base bound, which for this problem, this is a bit more of a challenging problem since the time horizon is longer. The back-base bound on success is around 70%. The success rate in simulation is around 78% on new indoor environments, and the success rate on the kind of real physical system tested on different environments is around 77%. Okay, so far in this talk, I've assumed that we have this underlying distribution over environments that is the same during training and testing. But of course, this assumption is not necessarily satisfied in real-world environments. So one really important question to try to address is what happens when the test environments are drawn from a different distribution than training environments. So maybe you trained your system to operate in indoor environments of a certain kind, maybe office buildings, and now you want to test in residential buildings. I think there are 2 kind of interesting questions here. So the first question is, can we detect when the robot is operating out of distribution? The second question is, can we actually learn policies that are robust to different distribution shifts? So I'm going to talk about the first question first. So if your robot is operating in some new environments, can it kind of automatically detect that there's been a distribution shift, in which case the robot could then potentially act more conservatively or cease its operations altogether and call for help potentially from a human. So again, I'll use this kind of drone example as a running example here. So we've trained the drone to do obstacle avoidance in a certain distribution over environments. We then deploy it in new environments that are potentially drawn from a different distribution. So for example, you can think of the training environments as having no wind, and then the test environments have some wind or potentially more clutter than you had during training. And the goal here is just to detect this, so not necessarily do anything about it, just detect when the robot is operating out of distribution. I think when we're thinking about this kind of OOD detection in robotic applications, there are two important criteria. The first one is ideally we'd like some guaranteed confidence bounds. So we want to be able to bound the false positive and also the false negative rates of detection. So false positive is when we say we're operating out of distribution, but in fact we're operating within distribution. The false negative is kind of the opposite of that. So when we say we're operating within distribution, but in fact we're operating out of distribution. The second important criterion, I think, is that we want to be sensitive only to distribution shifts that are actually task relevant. So maybe you can think of some environments where there are some small changes in the environment, but this doesn't impact the actual performance of your robot. In this case, we don't really care that there has been a distribution shift. We only care when the distribution shift actually has an impact on the performance of the robot. So the approach we've taken builds on the back-based machinery that I presented before. The basic idea is going to be to train a policy with a corresponding bound on the performance on the training distribution using back-based theory. And then if we deploy the robot on test environments and we see that the bound is being violated, then this gives us high confidence that the robot is operating out of distribution. Because if we were operating within distribution, we have a bound. If the bound is being violated, then that gives us confidence that we're operating out of distribution. So let me talk a little bit more about the details on how we do this. So the training phase, we use the exact same machinery that I presented before with back-based. So we train a policy and a corresponding bound that we get from back-based. In this case, we're using some more kind of recently developed back-based bounds that allow us to optimize a single policy, so not a distribution over policies. So these are de-randomized back-based bounds. And the cost we're using here corresponds to the distance to obstacles. So if you get close to an obstacle, that's high cost. If you're far away from an obstacle, that's low cost. And we're training a neural network that outputs actions based on sensor observations that correspond to depth images. During deployment time, we test our policy that we learned during the training phase on some small number K of new environments. And we basically observe or look for violations of the bound that we get from back-based. So if we see that in our test environments, the cost that we're incurring is higher than the guarantee we have from back-based, then this gives us high confidence that we're operating out of distribution. And you can use some concentration inequalities here to calculate a bound on the false positive rate of detection. So false positive, again, is where we detect that we're out of distribution, but in fact, we're operating within distribution. And as kind of you can see from this expression, as tau, which is the violation of the bound, increases, the bound of the false positive rate goes down. And you can also, using some different techniques, bound the false negative rate. So that's often what we care about for safety critical systems. So this is the probability that you think you're operating within distribution, but in fact, you're operating out of distribution. And finally, I want to point out that the scheme that I've kind of outlined here is only sensitive to task relevant distribution shifts, because we're only looking at the degradation of the cost. So there's no impact on the cost. If there's some distribution shift that doesn't actually impact the cost, then we're not going to detect that as a distribution shift. So we're only going to detect task relevant distribution shifts. So here are some results again on this drone example that I've been using as a running example. In the training phase, we don't have any wind gusts. And then we're testing in environments that have a fan. So you can see the fan at the bottom left of the picture. And we're increasing the amount of wind. So the wind here goes from about 0 meters per second to approximately 5 meters per second. And as you'll see, as the wind increases, the robot gets closer and closer to the obstacles. And that's the signal that we're basically relying on to perform auto-distribution detection. So here are some kind of concrete numerical results. So the x-axis here is the percentage of wind, so going from 0 to 5 meters per second. And the y-axis is our confidence that we're operating auto-distribution. So as we increase the amount of wind, the robot gets more and more confident that it's operating auto-distribution. Okay, so this approach that I presented relies on observing performance degradations or potentially even failures at test time in order to infer that the robot is operating auto-distribution. Ideally, we want to predict failure before it happens. So we've also considered this problem of failure prediction, where the goal is given some policy. So you can think of this as just some black box policy that someone hands to you. We are interested in training a neural network to predict if the policy will fail if you continue to keep deploying it, given some set of training environments where you can see what the policy does. If the failure is predicted, then we can potentially execute some emergency maneuver like stopping, for instance. And again, we've used pack-based theory to train a failure predictor with guaranteed bounds on the false positive and false negative rates of failure prediction. So I'll mention a caveat here. So with the auto-distribution detection problem, we can detect if the robot is operating auto-distribution potentially, but with this failure prediction problem so far, we've only applied it to problems where the robot is operating within distribution. So if there's a distribution shift, that's not something we can handle with this kind of proactive failure prediction. So the problem formulation here is you have some training distribution, some finite number of environments, and then you're deploying your failure predictor in new environments from that same distribution. So again, here are some videos on the drone example. So again, the formulation here is someone hands you a black box policy, and you want to predict if it's going to fail if you keep executing it. So in this case, the failure predictor stops the system, predicts that there's going to be a failure, and we tested the policy again to see what it would happen. So it would crash without the failure prediction. And these are different environments. This is a true positive. So in this case, the failure predictor predicts that you're going to fail, and the robot would have failed. This is a false positive. So the robot thinks it's going to fail, but in fact, the policy doesn't fail. True negative. So predicted not to fail, doesn't fail. Okay, so in this example, the true expected failure rate of the policy is around 25%. So we kind of handcrafted this policy to have a large number of failures. The bound that we're getting from our theory on the failure error rate, the failure prediction error rate, the false positive plus the false negative error rate is around 12%. The true false positive plus false negative rate of failure prediction on the actual hardware system is around 7%. And the false negatives on the hardware was 0%. So the false negative, in some sense, is what we really care about. This is when the failure predictor doesn't predict failure, but in fact, your robot is going to fail. And one thing I didn't mention is that we have a neat kind of theoretical way of trading off the relative false positive versus false negative rates. So for safety critical systems, you might want to have a very low false negative rate, but maybe you can handle a slightly higher false positive rate. All right, so I want to spend just a couple of minutes talking about the second question. So how can we not just detect when the robot is operating out of distribution, but actually learn policies that are robust to a set of different distribution shifts? I think one interesting question here is how do we even quantify this distribution shift? So one approach might be to look at the KL divergence or some other kind of divergence between the training and the test distribution. But this is not necessarily physically meaningful. So specifically, if you have two environments, let's say two distributions over mugs that have different color. So let's say one distribution has only mugs of red color, the other distribution has mugs of green color. In this case, in some sense, there's no distribution shift because the color is not relevant to the task that the robot is trying to do. But if you just look at the KL divergence, for instance, then you might say that there's a huge distribution shift. So one thing we've tried to do is learn some representation of environments, some latent representation of environments, where the Wasserstein distance between distributions captures only task-relevant variations in the environments. And then if you can kind of do this, if you can define some space of environments where the Wasserstein distance captures task-relevant distribution shifts, we can then perform distributionally robust optimization, so DRO, with respect to some Wasserstein ball around the training distribution. And it turns out you can do this via adversarial generation of environments. So you have some policy, you generate some adversarial environments in a specific way, and then you retrain your policy with these adversarial environments. So I won't go into the kind of details here. I'll just present some results in a manipulation context where we trained using this distributionally robust optimization process. And then we were looking at a kind of sim-to-real problem where we take the learned policy in simulation, deploy it on the real hardware system, and compare with standard baselines for sim-to-real, for example, domain randomization techniques. All right, so I just want to end with some directions for current and future work. So one thing that we're really interested in is scaling up the size of the training data sets that we used in order to improve the generalization bounds that we get from our theory. So in the examples I showed today, the bounds kind of range from around 90 to 95% for different problems. Of course, ultimately, we want significantly stronger bounds if we want to confidently deploy these systems in real-world problems. And I think partly it's a matter of scale. So currently we're operating kind of on the order of 1,000 training environments, and we're collaborating with some industry entities to scale up the size of the training data sets to see how far we can get in terms of the strength of the bounds. Another potentially promising approach is to use a kind of modular style of guarantees. So maybe we use these statistical learning theory techniques, PAC-based, just to provide guarantees on the perception part. And then we combine that with kind of well-known, well-understood planning techniques that give us some guarantees, assuming that the output of the perception system is correct. And then if we can do this, then we can combine the bounds to make an overall statement about the safety of the end-to-end system. Another kind of line of work we've explored is to embed prior knowledge in different ways. So if you can embed more prior knowledge, more inductive bias, then this can help improve the strength of the bounds that we get. And we've explored several different ways to do this. For example, if you have some approximate generative models over environments, you can incorporate that as a prior. We've also explored techniques combining these statistical learning techniques with techniques from robust control and reachability analysis. And we've also explored ways to do meta-learning, where we learn the prior using different kind of distributions that we have access to at the training time. So just to conclude, so I've presented this theoretical machinery based on PAC-based to provide some guarantees on generalization for robotic systems that have rich sensory inputs, such as vision or depth, and neural network-based control policies. And we can also do auto-distribution detection and auto-distribution generalization using this theoretical framework. So hopefully I've convinced you that there's some kind of exciting potential here to take these theoretical techniques and make some pretty meaningful guarantees on generalization and safety for deep learning enabled robotic systems. So if you're interested, we have a few papers on this topic. So our early work on unpacked ways was published at Coral and also IGRR in 2020. And since then, we've extended this and we have a few publications at Coral, RAL, and Europe's for the distributionally robust policy learning work, and also the auto distribution detection work and the meta learning work. So this is our group. So a lot of the work I presented today was done with Sushant Veer, who used to be a postdoc in our group and is currently a senior research scientist at NVIDIA working with Marco Pavone. And we have 7 PhD students in the group and a number of undergrad students as well. All right, so I'll leave you with this conclusion slide and take any questions you have. Thank you.
Thank you, Ani, for the great talk. Let's open the stage for questions. So you can either raise your hand and then mute yourself and ask, or also ask in the chat, and I will repeat the question to the speaker.
Ani, yeah, thank you. Thank you very much for the talk. Very interesting. Lot of things. One question. So your policy is, so you use the vision, the images, right, as input?
Yeah.
Is single image or is multiple images?
Yeah, so usually we use a short history of images. And you can potentially use a recurrent network, or you can just stack the images and just use a feed-forward network.
I was wondering how you did like a rate control and things like that. If you...
Yeah. So you need some history to keep track of the state in terms of derivatives.
Mm-hmm. Now, have you tried something? So this one, right? So as you probably know, if you have an environment which is in which the obstacles are disjoint circles, then you can just go down some, get closer to the objective, and then you will get there, right? Clearly going around the obstacles, right? So have you tried something that is a little bit more challenging from the point of view of the motion planning, right? So we're just trying to get closer to the obstacle is not enough, right? So for example, you have dead ends and things like that.
Yeah, I think the closest we came to that was with the quadruped navigation example. So in this case, there are some. I guess this kind of like kitchen environment is a bit of a cul-de-sac. So the starting point and the ending point are marked with tape, and so the robot kind of goes one way, and then kind of turns around, and then goes towards the goal. So in this case, these were more realistic environments and not just a free space punctuated by cylindrical obstacles. And these have like some like dead ends or cul-de-sacs. I guess were you thinking something more complicated even potentially?
Yeah, so something where I don't know. Something in a sense where probably the path to the goal is not, in a sense, easily guessed, right? So it's not enough, try to get closer to the goal, then I'll figure out, some way, right?
I see. Yeah, I think that would be interesting to do. I think that the general approach would definitely still be applicable, but I guess it would be interesting to see like what kinds of bounds we get from the theory. So I guess in this case we were like mostly picking kind of relatively constrained problems to see how far we can get in terms of the guarantees in terms of generalization for the neural nets.
Right, but I think that your main your definition of failure is, you're focusing more on not doing anything, don't get killed, right?
Yeah, right.
And that will still apply, right? So
Yeah.
as long as the obstacles are not trying to grab you or something.
Sure. Yeah.
Okay. Okay. But when you had the disturbances like the wind, right? So there was something that you were not modeling, right? So it was something out of a distribution.
Yeah, exactly. Yeah.
Right.
So there we were basically seeing. So we had a guarantee on the training distribution without any wind, and then because there was wind in the test distribution.
But you still have a notion of closeness to distribution, like you have something like the KL divergence or something like that, right?
Yeah, so for the out of distribution detection problem, we don't need any kind of metric on distribution.
Yeah, because you just say that that you're out of, but there is a probability delta that even if the distribution is correct, or the environment is in distribution, you still get things wrong, right? So
yes, yeah. So we can only give a confidence that we're operating out of distribution, and that confidence depends on how much of a violation you see.
Right.
So if you see a small violation, then you might still be within distribution because there is some probability that you're gonna see a violation even within distribution. But if you see that there's a lot of violation, or there are like violations kind of multiple times, then that gives you high confidence that you're operating out of distribution.
Yeah. Okay. Yeah. Thank you.
Hi. I have a question, and so the premise is that I'm not really familiar with pack theory. Since I looked at it many years ago, but could you go back to slide 40?
Sure.
So if I understand correctly, P0 is the training distribution.
So
and
P0 is actually the prior distribution over the policies. So not the training distribution over environments. Does that make sense? So the
that is what I'm a bit confused because I don't understand this. I didn't understand this part. So maybe tell me what I missed.
Yeah, sure. So the distribution over environments, so the distribution over like obstacle environments, let's say, is what I was calling D. Let me just go back here. Yeah, so this slide explains the kind of general structure of the learning algorithm. So P0 is the distribution, the prior distribution over your hypothesis space, so over the policy space. So these are, you can think of this as a distribution over the weights of your neural network that you specify before observing any data. And then P is the posterior distribution over policy. So that's the thing that we're trying to learn. So I just go back to the slide 40. Yeah, so in this case, the bound, like the term in the bound that's the KL divergence, is the KL divergence between the posterior and prior on the policy space. So,
okay, so you're saying that, so you said P0 is my prior, that's like a regularization, what I guess, I might choose to do. Then when you say choose a posterior, means like do the training actually. And you get, but okay, but the training could be stochastic. So anyway, I get a distribution of policies.
Exactly.
And now, okay. So now C of D is the actual environment. So you're saying that, okay. So I mean, I'm a bit confused dimensionally, right? Because on the second term on the right-hand side does not have the dimension of the cost, unless the cost is something special.
So the cost is bounded between 0 and 1. So you can think of it as a probability,
Okay. So I mean, okay, so it's very interesting. Like so what I don't see here, so there is no bound between the training and the deployment environment. It doesn't appear here.
The assumption in this bound is that the training and test distributions are the same distribution.
Okay.
But yeah, I guess the main challenge here is that we don't know what that distribution is, right? We just have the training data set, like finite training data set that is drawn from this training distribution, which is the same as the test distribution. So that's the relationship. We actually have a different bound where it was kind of similar to what Emilio was saying. So if you have a test distribution that's different from the training distribution, but you know that the test distribution is going to be in some KL ball around the training distribution, we have a different bound that basically adds another term that captures how far away in terms of KL divergence, let's say, the test distribution could be from the training distribution.
Mm-hmm. So, but I don't understand where the trick is, right? Because there's true expected cost. It depends on D that you never see. So you don't know D at all.
Yeah, you don't know D at all, but S is drawn from D, right? So the training data set.
Okay.
That's the kind of connection. Yeah.
I got it. Okay.
Yeah, so we don't have direct access to the distribution D, but we have indirect access in the form of the training data set, which is drawn from that distribution.
So N is the number of times you're drawn from the distribution.
Exactly. Yeah.
Okay, the other thing, I was very interested when you said this bound is task dependent. And you said something like, I will not tell you about this, but it seems very interesting to me. So if you could expand on that.
Okay, the Wasserstein one?
Yeah, so what's the idea here? And the other thing that seems like magic, I don't understand how you could generate these adversarial environments.
Yeah. Okay, so I guess there are definitely some details here. So the main motivation was to capture task relevant shifts in the distribution. So the example I was giving is if you have two distributions where everything is the same but color is different, and sometimes we want to say that they're really the same distribution because there's no task relevant shift. So what we're doing here is we're using something like a autoencoder structure to learn a latent space, so a latent representation of environments. So with objects, we use something like PointNet. If you've seen that, these kind of like 3D architectures that takes in a point cloud, maps it to a latent representation, and then decodes it. And what we're doing is we're learning a latent representation such that closeness in the latent space corresponds to closeness in terms of cost. So we assume that we start off with some kind of base policy that has a certain performance. And then we learn this latent representation such that if you have two objects that are kind of a similar distance or close in distance in the latent space, then they should have similar costs. So that's how we're training the latent representation. And I guess what this does is the metric, so the distance in the latent space captures how far away different objects are, different environments are in terms of the task, so in terms of the cost. And so then if you define a distribution over that latent space, which induces a distribution over environments, then the Wasserstein distance captures a task relevant kind of notion of distribution shift. So that's the main intuition. In terms of your other question about how do we do the adversarial generation of environments, so that we're doing by like optimization in the latent space. So from the latent representation, we can predict what cost a certain environment will incur. And so we just do like gradient ascent, basically, so to try to find a latent kind of latent representation that will lead to an environment that has a high predicted cost. So that's the rough idea. Like once we have this latent space, we can like generate environments by just choosing different points in that latent space.
But this distribution also depends. It's specific not only to the task, but also to the agent, to the policy, right?
Say that one more time. Depends on.
The cost is a function of the environment and the policy, I suppose, right?
Yeah. So we have a kind of a recursive scheme. So we start off with some policy. We do this kind of latent representation learning. We then do the adversarial generation of environments with a particular policy that we have right now. We retrain the policy with the adversarial environments. And then we have a new policy, and we can do this until we have some kind of convergence.
Okay, just to understand. So imagine that there's this environment with two cups, and I have a robot that has both a LiDAR and a camera. But then I have two agents, one that only uses the camera, the other only uses the LiDAR. So maybe the camera-based agent is sensitive to the texture, or to the color of the cups. And so the adversarial examples would be ones where the cups kind of change color. But the LiDAR one is sensitive to not to the color at all, but only to the shape. So the adversarials would be like different size cups or different position of the cups.
Exactly. Right.
Okay.
Yeah.
That's very, very cool.
Thanks.
Thank you.
Good. Other questions?
Is there any other question?
Hello.
Go ahead.
I have a question on the page 20.
On the which one, sorry?
20.
20. Yep.
About the sensor, I do not know how do you deal with the sensor information, or how do you process the sensor signal?
Yeah. So I guess there's two parts to that. One is how do we simulate the sensor? So we're using for most of these examples we use a PyBullet or Gibson, which does kind of pretty photorealistic like renderings of let's say vision. The second part is how do we process the sensor observations. So that's where we're using a neural network architecture. So the specific architecture depends on the specific problem. So if you have a point cloud, then typically we use something like a PointNet architecture. If you're just using RGB, then we use convolutional neural networks to take the raw image and then process that into to actions. Does that answer your question?
Yep. And do you also use some sensor fusion, like the deal with some noise?
Yeah, so in these examples, we were just training everything end to end. So there's some kind of implicit sensor fusion, but that is learned. So we're not explicitly like implementing a Kalman filter or anything like that for these examples. You definitely could. So you could have some pipeline that does sensor fusion in a way that you specify. So using a particle filter or a different kind of filter, and then take the output of that perception module and then learn the rest. In this case, I guess just for kind of conceptual simplicity, we're training everything end to end. So just going from raw sensor observations to actions.
Okay, I see. Thank you very much.
Yep, no problem.
All right. Thank you all for the great questions. I think it was a great talk and created a lot of interesting discussions. So thank you all again. Thank you again, Ani, for the talk.
Thanks for having me.
I will follow up with the video once it's edited. And thank you all for participating, and see you all next week for the next Autonomy Talk.